Okay, so I want to take a look at some basics of geometry that we're going to need to get us going in our trigonometry unit here. The first thing we start talking about geometry, the most basic symbol in geometry is that thing right there. It is called a point. And a point is simply a location. And it has 0 dimensions. Dimension, by the way, a dimension is a direction in which things can be measured. Dimensions must be perpendicular, make right angles with each other. So now we can take that point and we can move it in a single direction. We did this last semester. That was how we created a length. The length of that was equal to the distance we moved. And of course, that is technically called a line segment. And that line segment now has 1 dimension. So that 1 dimension can be thought of as we can measure it in one direction, or we moved in one direction to create it. Now, last semester we talked about taking that line segment and moving it in a second perpendicular direction. That would be like this, to create, in this case, a rectangle or an area. Well, right now, we did that last semester, finding areas and volumes. Right now, what we're interested in is taking that point and moving it in a single direction and continuing to go on forever. What we create there is called an array. An array is completely defined by 2 things. 1, that starting point. And 2, the direction that it goes. So let's define that direction just a little bit. Direction comes off of navigation. Where in navigation you have a grid that's set out. And often, like if you're looking at aerial navigation, usually your 0 point is north or south, depending on what hemisphere you're in. Mathematically, for direction, we usually use our 0 point as that east direction. That is 0 degrees. And of course, we go around, this would be 90 degrees, 180 degrees, 270 degrees, and then 360 degrees puts us back at 0. So this ray has that starting point at the center of the grid, and that direction, I'm just going to throw a number out here. Let's say that's 19 degrees. So that defines that ray. Well, let's say we go back to that same starting point right there, and we move in a different direction. Well, that ray is defined by the same starting point. When you have a starting point that is the starting point for more than one ray, it is called a vertex. And that ray has a direction. Let's say that direction is 51 degrees. Of course, those 2 rays with a common starting point or a vertex form what's called an angle. The size of that angle is just the difference in the direction between the 2 rays. 51 degrees minus 19 degrees is 32 degrees. That's a 32 degree angle because there's 32 degrees difference in direction of the 2 rays. That's the technical definition of an angle, and kind of an old definition of an angle. Used more commonly back when the general population, many people in the general population had a little bit of an idea of how navigation worked. Bless you. No, navigation is kind of a lost skill these days with modern, compass and GPS and all that stuff. I mean, I guess a lot of you have probably never even used a paper road map. Am I correct? Yeah. You do have one? Yeah. I actually still have one of the big national road atlases in the back of my car, but I haven't pulled it out for probably 2.5 years. So to define angles now, we look at it in terms of rotation. If I am looking in one direction and I spin all the way around, how far have I rotated? 360 degrees. One complete turn or one complete circle is 360 degrees. If I am facing a direction and I turn so that I am facing exactly the opposite direction, how far have I turned? 180 degrees. How'd you get that? Half of 360. It's a fraction of the full turn. The fraction would be 1/2. If I am facing one direction and I turn so that I'm facing exactly to the left of where I'd been before, how far have I turned? 90 degrees. And again, that was found as a quarter of a full turn, right? 1/4 of 360. Of course, we also know that is referred to as a right angle. That little box in the corner indicates, that little square indicates that it's a square corner, a right angle. So our angles now, we've adjusted the definition to just be that fraction of a full turn. If I have an angle like this and I tell you that that angle is 63 degrees, what that is saying is that is 63 360ths of a full turn. Full turn, full circle, however you want to look at it. If I just have that segment like we created in the first place there, I name that segment from its endpoints. There might be other points on here. There might be a point D in here somewhere. But that segment is named by its endpoints, A and B. So if I write A and B with that little line segment drawn above them, that means segment AB. But if I just list it as AB without that symbol above it, what that's really saying is the length of segment AB. Or the distance from A to B, if you look at it that way. That ray that we had. Now over here, by the way, I could have named this segment BA. It wouldn't have mattered, does it? It doesn't really matter which endpoint comes first. There's no order. On our ray, however, we use that little ray symbol, and the first letter has to be that starting point, A. Now the second letter can be anything. Let's say we have points A, B, and D here. We could name that ray AB or ray AD. It doesn't matter. The first letter has to be that starting point. The second letter can be any other point on that ray. Now, we're going to talk a lot about lines. Remember, a line continues on forever in both directions. Well, in practice, that's not really very practical. We don't use a line. We don't have things that go on forever in both directions. Rays occasionally have things that start and go and never stop, but the true line is not real practical. So most of the time when we say line, what we're really talking about is going to be a line segment. But let's look at some of our relationships between lines. How would you describe these two lines? They intersect. Very good. And intersect just means they cross. And technically, they cut through each other. How would you describe these two lines? Parallel. So we know parallel when we see it. How would you define parallel in words? Okay, there's the big thing. Never intersect, never touch. And that's the definition that most people know of parallel lines. But that's when we're restricted to two dimensions. On a flat piece of paper, just saying that two lines never intersect is enough to know that they're parallel. The only way they can never intersect is if they're parallel. But in three dimensions, that's not strong enough. And of course, we live in a three-dimensional world. Let's say this is a line and this is a line. Do they ever intersect? No. Are they parallel? No. So to be parallel, it has to be a little bit stronger in 3 dimensions. The technical definition of parallel, well, the technical wording is everywhere equidistant. All that really means is always the same distance apart. So we have then a third special relationship we're going to look at, which is like this. What's that? That is, as we discussed, perpendicular. They intersect in a right angle. And of course, we know if 2 lines intersect and make 1 right angle, they make 4 right angles. There is actually a name for this up here, by the way, lines that intersect, but they're not perpendicular. Or for the 3-dimensional example I showed you where they don't intersect, but they're not parallel. That's called oblique. Okay, so do we have video of you doing the dance? I'm gonna volunteer. Okay, so if we have these parallel, in fact, we don't even have to have parallel lines. We can have any 2 lines, 2 or more lines, in fact, that are cut by another line. That line that cuts them is called a transversal. Well, on regular lines where it cuts across, it doesn't do anything special. But when it cuts across parallel lines, it does some really special things. Though some of this is going to be a review from last semester. If I tell you that this angle here is 54 degrees, what's this angle here have to be? 126 degrees. Where'd you get that from? 180 minus 54. Good. Those 2 angles we know have to add up to 180 degrees because they make a straight line. Remember what we call that? Supplementary. Supplementary angles add up to a straight line. Side note, by the way, what do you call 2 angles like this that add up to a right angle? Complementary. You got it. So anyway, what's this angle here have to be that I just marked? 54. Why? Yeah, there's actually 2 reasons why. One, it is also supplementary to 126. But remember, we defined this last semester. Those 2 angles are what we called vertical angles. They're across from each other on that same vertex, that same intersection. When 2 lines intersect, they only form 2 angles. 2 angles that are they're either equal or supplementary. Well, now we have this second line down here. But remember, since these are parallel, if I were to slide that one up here, it would lie right on top of this other line, wouldn't it? So what that means is this angle here is really just that one, 54 degrees. How about this angle here? Just that one, 126. And of course, 54 and 126. Now, if this were a formal geometry class, there'd be a lot of vocabulary being introduced here. There would be these 2 angles, which are called corresponding angles. There would be this one and this one, which would be called corresponding interior. Corresponding angles are on the same side of that transversal. Interior means they're both inside or between the parallel lines. These 2, which would be called corresponding exterior. There would be these 2, which would be alternate interior. Interior, again, meaning between the parallel lines. Alternate meaning on opposite sides. Which, no, we're not. We don't give a crap about all that vocabulary. All we care is that you know when two parallel lines are cut, it's hard to have one parallel line. When a set of parallel lines are cut by a transversal, there are only two angles formed. So if you know one of those angles, like we started with the 54 here, all the other angles must either be equal to it or supplementary to it. Very good. Now we also know, by the way, that a triangle, if I tell you that this is 86 degrees and this is 39 degrees, what do we know about this angle here? Careful. 55 degrees. How do we know that? They have to add up to 180 degrees. So with all that knowledge put together, I'm going to have you guys try one. I'm going to tell you that this angle here is 50 degrees. I'm going to tell you that this angle here is 30 degrees. I'm going to tell you that this angle here is 35 degrees. I want you guys to find for me those angles. It really won't take that long, I swear. Okay, so let's take a peek here. Let's start with the easy ones. What's angle 12 here have to be? 150, very good. 13, 30, 14, 150. Now, are there any other angles that must also be 30 because this one is 30? 27 and 24. Are there any other angles that must be 150 because this one is 150? 23 and 25. Yeah, it is. Nope. Oh, wait, you are absolutely correct. This is not 150 down here. This is 115. This is 115. Good catch. Because there's this extra little angle taken out. What's this one have to be since we're here? 35. That's vertical 35. So the correct answer is what Ryan said. No, there are no others that could have to be 150 because this line does not intersect here by itself. There's another line that takes angles away from it. Let's go with the other one we were given. We have 50 here. Are there any other angles that have to be 50? 3, 20, and 22. What's one have to be? 130. Any other angles that have to be 130? 2, 19, and 20. Very good. 21. Okay, so from there, I can find angle 5. How can I find angle 5? 30 and 35, make that 65. That makes this one 65. Now I can find angle 8. It must be 65 because those three angles have to add up to 180 because it's a triangle. So that makes 10 65. How about 9 and 11? Yeah, 115, the supplement of 65, right? Now what do I know? Well, 4 and 6 are 115, you are correct. I know I'm leaving off the degree symbols, but they're kind of crowded, so I don't want to cloud anymore. You said what about 18, Liam? 18 has to be 80. Why do I say 80? 65 and 35 add up to 100, right? So that's 80. So 16 is also 80. 15 and 17 are 100. And that should be it, I believe. Not so bad, huh? Okay. So we've got that one complete turn is 360 degrees. But it can actually be divided up into angles a little bit smaller than that. 1 degree, of course, is 1/360th of a complete turn. But what if we need to go smaller divisions than that? Well, 1 degree is divided up into 60 minutes. The symbols would be 1 degree equals 60. We use a single hash or a single quote for minutes. Smaller than a minute. 1 minute is divided up into 60 seconds. Again, the symbols 1 minute equals 60 seconds are marked with a double hash. Now, for you guys being in construction, you can see the possible confusion here because that's the same symbol as for foot and that's the same symbol as for inch. So you got to be careful to make sure you know whether we're referring to an angle or a length. Now, to be honest, in construction, you aren't going to do anything smaller than a degree in your measurements. Unless you get into like precision, like steel work or anything like that, then you may end up having to do finer. I have never, even in real precision machining, I've never seen anything measured down further than a minute, just because the molecular errors in materials, the individual atoms within the materials can deflect enough to throw you off by more than a few seconds of a degree. So to measure anything down more precise than a minute is really tough to do. To be honest, most of the time I see it down to like five minutes or 15 minutes is a standard. But they're there mathematically, and yeah. So let's take a look at that. Let's say we have something that is like 18.375 degrees. And let's convert that in degrees, minutes, and seconds. This is going to be very similar to our feet, inches, and sixteenths conversion. This is 18 degrees. That part in front of the decimal point doesn't change. What do we do with what's after the decimal point? Times 60. There's 60 minutes in 1 degree. So the degrees cancel out and we are going to be in minutes, which is going to give us 22.5. That's now minutes. What do we do with that? Now we take out our 22. And we take the 0.5 minutes and we convert it into seconds. So we subtract 22 and we take that remainder times 60 again, make it 30 seconds. So that's 18 degrees, 22 minutes, 30 seconds. Make sense? I'm going to have you guys try one quick. 42.783 degrees. Convert that. Now the notation here is DD. DD stands for decimal degrees. You are going to convert it into DMS, which is degrees, minutes, and seconds. So I'm going to give you about 30 seconds to do that conversion quick. So we take off the 42. That's degrees. So we'll subtract 42. Then what do I do to the 0.783? Times 60 is 46.98. That's 46 minutes. Then what? Subtract the 46 times 60. 58.8. Now, in the seconds, it is okay to leave it to one decimal place. And if you do that, that's fine. But like I said, I've never seen anything measured down to a single second, much less down to a tenth of a second. So we're just going to round that to 59 seconds. Any questions? Nanoscience. Yes, pretty much. There are some lasers, laser items, reflections and stuff like that where you can deal with it, but it's very, very subtle. Light refractions and things like that. Let's go the other direction from DMS into DD, decimal degrees. So let's say I have an angle that's listed as 23 degrees, 14 minutes, and 36 seconds. How do I convert that back into degrees, minutes, seconds? Well, I start with the seconds, or sorry, convert it back into decimal degrees. I start with the seconds, the 36, and I do what? Divide by 60. That is 0.6. That is now minutes. So I can add in my 14 minutes. So that's 14.6 minutes. What am I going to do with that? Divide by 60 again, makes it 0.2433 degrees. So that's 23.2433 degrees. Standard is usually 3 or 4 decimal places for decimal degrees. Unless otherwise stated, go to 4 decimal places. Go to the 10,000th of a degree. In your notes, I'm going to have you guys try one. 37 degrees, 29 minutes, and 18 seconds. Convert that into decimal degrees.
Usually rocket surgery. Yeah, rocket science brain surgery. Never done rocket science.
Okay, so this is 37 point. Let's see what we have to do here. We start out with the 18. What do we do to it? Divide by 60, and then add 29, and then divide by 60, and then add the 37 to it. Good. 0.4883 degrees. Not so tough? Well, how about this? "17 degrees, 43 minutes, 29 seconds, plus 14 degrees, 31 minutes, 58 seconds. 29 plus 58 is 87 seconds, but that is bigger than a minute. That's 1 minute and 27 seconds. Very good. So we keep the 27, carry the 1 minute. So 43 plus 1 is 44, plus 31 is 75 minutes, which is 1 degree with how many minutes left over? 15. 1 and 17 is 18, plus 14 is 32 degrees. It's just a matter of carrying and remembering that when you carry 1, you're just taking 60 out of it. Kind of like with measurements. How about this one? $29 minutes, 29 degrees, 15 minutes, 43 seconds, minus 11 degrees, 51 minutes, 47 seconds. What do we do with that? Well, we start on the right and work our way back to the left as always. When we see 43 we can't subtract the 47 from it. So we're going to borrow from the 15. That'll be 14. This becomes what? 103, because the one that we borrowed becomes 60 seconds. So now we can subtract. This gives us 56. Now 14 minus 51 doesn't work, so we're going to borrow from the 29, make it 28. This is now 74. 74 minus 51 is 23. 28 minus 11, 17. Not so bad. How about this? Multiplying. We do 6 times 41 is 246 seconds. How many minutes can we get out of that? 4 minutes. 4 times 60 is 240. So how many seconds are left? There are 6 seconds. So now we got 6 times 27, which is 162. Plus the 4 is 166. How many degrees can we get out of there? 2, right? 2 times 60 is 120. So there are 46 minutes left over. 6 times 4? 24 plus 2 is 26 degrees. What do you think? Just got to remember your conversions, yes. How about if we have 39 degrees, 57 minutes, 24 seconds, and we're dividing into 6 equal pieces. 6 goes into 39 how many times? 6. That's 6 degrees. 6 times 6 is 36 degrees. So how many are left over? 3. Now just like with measurement, before we bring down the next unit, what do we have to do to the 3 degrees? 180 minutes. So we bring down the 50, now it's 237 minutes. 237 divided by 6 is 59. Right? 59 times 6, that's not right. 39, right? 39 times 6 is 234. Does that look right? We subtract, there are 3 left over. Before we bring down the 24, we have to convert the 3 into 180. Bring down the 24, it is 204. 204 divided by 6 is 34. So 6 degrees, 39 minutes, 34 seconds. What do you think? Beautiful stuff? You know, it's not that hard to do, really. That's really a pain. Well, I mean, and I'm going to be totally honest with you right now, the chances of you ever actually using this are pretty slim. No, I mean, it's in here because if you ever were to go on to like an engineering degree, it's in the math coursework for those. But if you stay in the construction field, you're in beyond a degree. I mean, realistically, if you can measure within 1 or 2 degrees in construction with wood, that's dead on. Geometry, usually 1 degree is really your tolerance. On your big textbook, page 455, the unit exercises, the odds. That just kind of goes over some vocabulary. We went over most of this vocabulary and how to name things, but you may have to look back in the chapter a little bit. It's a lot of vocabulary and the symbology. What how do you put a symbol for a line segment or array and stuff like that, which most of you have seen before. I'm not going to take time to lecture on that unless we have questions next week. But then page 461, exercise 20-4. Page 464, exercise 20-5A, and page 467 through 468, exercise 20-5B. That's a lot of problems, but this is really kind of preliminary. We're getting the vocabulary and the symbols and the meanings of things down before we jump into the trig. All this work with angles is preparing us to start talking about trig. There's some things we have to cover. We have to talk more about circles before we can do trig, and a couple other preliminary things. We're good. A lot of people think trig is all about right triangles, and that's what we apply it to, but trigonometry actually comes from circles.